Thank you, Jake, and thanks for having me. Is there an award for the longest title? What I will try to do today is talk a little bit about the present day and future importance of understanding pore space distribution in sedimentary rocks. And I'm going to use as an example something that we have been working on for a while now. I will use meandering rivers to show how we can understand this better using stratigraphic forward modeling. And before I move on, I'd like to thank my collaborators and co-authors, Jake Kovold, Paul Durkin, Steve Hubbard, David Morrigan, Richard Sack. This is a session on sustainability, so I think it's a must to look at this fine analysis by Randall Munro of XKCD fame. And I think this is actual data showing the occurrence of the word sustainable going back in time. And there is a present day data point, and he extrapolated this into the future and said that 90 years from now, all sentences are just the word sustainable repeated over and over again. And I find that very funny, but there's a good reason and a very serious reason for the word sustainable being used more and more. Along those lines, I just put together some thoughts on sedimentary geology in the Anthropocene and how we sedimentary geologists can try to help to address these serious problems related to sustainability. So let's, and this is kind of a personal list, so don't, I probably left out many things that are equally important. What are some of the challenges? Well, the coastal systems are going to are responding as we speak to sea level change, to larger storms, subsidence due to damming of rivers and reduction in sediment supply. Rivers and lakes respond to changes in precipitation patterns and sediment discharge again. Plastic pollution is widespread, and sedimentologists know about how particles move through the hydrosphere. And finally, but maybe most importantly, it is increasingly important to understand the nature of pore space distribution in sedimentary basins. And there is no need to convince anybody in this room probably that oil and gas are still important and will be important in the near future. And it's even more important nowadays to have good models of the subsurface to extract hydrocarbons efficiently. Also, obviously, water, pore space distribution is important for water resources, and carbon, and it's important for carbon sequestration as well. And that's something I want to expand upon a little bit in the next few slides. But before I do that, I think there are also, in addition to these potentially depressing challenges, there are also great opportunities today for sedimentary geologists. So, for example, the availability of remote sensing data like satellite imagery, LiDAR, seismic reflection data, drone imagery, it has just exploded, and we have more data potentially than we want. We just need to take the time and develop the tools to analyze these efficiently. Also, I see a convergence of the study of Earth surface processes with stratigraphy and sedimentology. And when I was in graduate school, I didn't even study formally geomorphology, and I believe, and I think this is becoming an obvious thing, that there is no good understanding of stratigraphy or sedimentology without knowing geomorphology. And let's be honest, geomorphologists can get away without knowing stratigraphy, but it doesn't work the other way around. And finally, I'm very excited about the availability of a wide range of open source software tools and for data analysis and modeling. And also, linked to that, these words are sometimes used as buzzwords, but this is an extremely important development in the last few years, and it will have impact on the future of sedimentary geology as well. So next, I want to expand on some of the things I actually know about a little bit, and that is pore-space distribution, and specifically related to sequestration of CO2, and touch a little bit on all these opportunities. So why is sequestration of CO2 a potentially very important subject to us sedimentary geologists? This is obviously a temperature record going back in time until about 60 million years, back to the Eocene. And what you can see on the right, there is 2005. I think this line is 2018. No, actually, that is 2100. Anyway, these projections into the future are the representative carbon pathways, concentration pathways that the ICCP developed, and that is the most pessimistic one, RCP 8.5. And the idea here is that if we do business as usual, then this is basically this red projection is the one that we are going to land on. And that essentially means this paper published in Proceedings of National Academy of Sciences, that this paper essentially says that this means going back, certainly back into the Pliocene, but this red area essentially takes us back into the Miocene and Eocene. And that would not be a good thing. In the same paper states that reversing this, essentially what we are looking here is a reversal of a multi-million year cooling trend in less than 2 centuries. So there's increasing agreement among many experts that carbon capture and sequestration has to be part of a solution. I'm just going to quote these authors who said that carbon capture and sequestration employed on a global scale can sustain a transition period in the world's energy use and help mitigate alarmingly high CO2 levels in the atmosphere. Some may argue that this technology will provide the excuse to prolong the use of fossil fuels. Others, including us, argue that we need all the help we can get in reducing CO2 emissions, and that by implementing CCS, we can exploit an already available fossil fuel infrastructure. And I would add to that we don't only have, we as energy industry people, we don't only have the infrastructure, but we also have the know-how how to do this. Just a few interesting things that many of you probably already know about CO2 and its sequestration. One is that the good news is that as you inject CO2 deeper into the ground, close to about 1 kilometer depth, it becomes supercritical, and its volume reduces significantly, and then its behavior is not that different from hydrocarbons. And we know a lot about that kind of behavior in porous media. Also, those concerns that would say that there's not enough pore space to inject this much CO2. If you look actually at the amount of water injected, I think this was in 2012 or 2013, something like that. The amount of water injected in the US roughly equals in scale the amount of CO2 that would need to be injected if we used all the point sources in the US. So the scales are enormous, but we have been dealing with these scales in the energy industry for a long time. Another interesting aspect of CO2 is that in contrast with residual oil saturation, which is not a good thing, residual CO2 saturation is a good thing, because it can be actually an efficient way to trap a large plume of injected carbon dioxide, just because these residual bubbles that stay behind. So this is an example of a sandstone that has significant residual saturation of CO2. And one of the implications of this is that all the fine, interesting sedimentary details in heterolithic rocks that we sedimentologists are very interested in are likely to become more and more important in the future as this becomes a big business. At a larger scale, we will need to build models just like we are building reservoir models today. And this is an old paper showing how this is a model of a channel with some splays and so on. And they injected, in the model, they injected carbon dioxide to look at how the saturation evolves through time. So we will need to build reservoir models not just for oil and gas, but also to understand how CO2 will behave in these models. And to state the obvious, nowadays we know to build better looking, more realistic models. And so that's what I'm going to talk about the remaining time of my talk. Finally, I will talk about something I know something about. And that is modeling pore-space distribution in meandering rivers. And here is one LiDAR image from the Ivalo River in Finland. And what we want to do, and most of what I'm showing here is not exactly new. People have been building great models of meandering systems before. But what we want to do is to build some point bars, of course, counterpoint bars, and oxbow lakes, and see how this impacts fluid flow. But before we get there, one of the important things is to understand the kinematic evolution of meanders. And here is a simple and old model which shows how first we need to understand curvature, and then how curvature impacts migration rate in meandering rivers. And the key point here is that migration rate is not a function of local curvature. It is a function of the weighted sum of upstream curvatures times constant. And this integration, this weighted sum, results in a phase shift between the black curve, which is curvature, and the red curve, which is migration rate. This is a fundamental property of meandering, and one of the aspects, one of the many aspects, implications, is that there are locations along the river, like these locations, highlighted in green, where the two vectors are actually pointing in different directions. And these locations are essentially what have been called before counterpoint bars. So we have put together a little Python package that can be used to build these simple meandering models, largely based on this classic paper by Howard and Knudsen. And you can see one of the outputs here, a very long-term evolution, of course, lots and lots of oxbows. If you want to paint it over with vegetation, then you can do that. One of the questions, of course, whether this simple convolution model actually works in nature. And as I already said, we have an enormous amount of fantastic data, like satellite imagery, and we can look at time-lapse animations like these. And we can extract river banks and river center lines and try to test our models. In fact, we can go further than just extracting center lines and banks. If we do that over and over again on the same image, then we can actually recreate, not recreate, but try to extract morphologies of channels like I'm showing here on the Trinity River here in Texas. Also, we need to estimate migration rates, and one good way to do that is to use this algorithm called dynamic time warping, which links every point on centerline 1 to every point on centerline 2. And we have a very fine resolution and decent estimate of local migration rates. So we use these approaches to test this model on 7 rivers, nice meandering rivers, unaffected by humans in the Amazon basin. And we found that there is a remarkable correlation, a very good match between migration rate shown in green at the bottom and curvature shown in blue at the top, if we take into account this idea that the migration rate is actually shifted downstream from curvature. And this phase shift between curvature and migration rate is also linked to the autogenic generation of counterpoint bars. And historically, counterpoint bars have been linked to confined rivers like this one in Bolivia, where these are, the red lines are locations of confinement, so the erodibility is low over here, and that's why this bend translates downstream. And the result of that is deposition of finer grained sediment along here and over there. And in outcrop, these rocks look like what you see on the right side. Dark colored rock here obviously is very mud rich. So it's important if you want to understand pore space distribution. The reason why these counterpoint bars can develop in any system that is meandering is that coming back again to this phase shift between the point of maximum migration, which is the red, and the point of maximum curvature, which is black. So if you have a short band like this one, which developed after cutoff, then the point of maximum migration falls on the downstream limb of the band. So this band is going to translate a lot, whereas this big, long arc is going to expand. So this is a fundamental reason for development of translation in meandering systems. So if we look at a natural example, this is a place studied by Darrell Smith and others in Canada. You can see here a translating bend, this one, and I can paint in these cores that they have collected, and you can see how it goes from pretty good sandy material to almost no sand over there. We can also paint in the point bar and counterpoint bar and the vectors of migration and curvature, and you can see again that the counterpoint bar mathematically occurs where these vectors point in opposite directions. If we look at not all counterpoint bars are 100% mud. Of course, this is an example that one of our students is studying in the Trinity River in Texas. You can see how heterolytic, there's a lot of sand here, but there are all kinds of mud drapes. To state the obvious, this is not tidal. It's entirely related to counterpoint bar deposition. How can we get better at estimating where these heterogeneities are? we can try to quantify the location of these counterpoint bars by using this measurement called the bar type index. So if this is a river center line, we can plot the curvature. There is the migration rate in green. Now if we multiply the two curves, I get the red curve. We call that the bar type index, and the idea is that whenever this index goes negative, like here, here, and here, and here, those are the locations where you expect translation and counterpoint bar formation. So to illustrate that a little bit better, the brown spots are going to be the preferential locations for counterpoint bar development. So let's look at it. Let's look at a quick model of a cutoff, which generates a sharp bend, which is rapidly translating downstream, and you have all these blue zones where you have more heterogeneities probably. So you can use models like this to predict longer-term evolution of rivers and predict distribution of the heterogeneities. This also happens in nature related to these cutoffs and other disturbances, other perturbations, if you want. And you can even see how a lake is forming over here in the shadow in the wake. That was the word I was looking for, of this downstream translating meander. If we let the model run for longer, then we get images like this. Of course, we want to go 3D, and we want to understand how fluid flow actually behaves in these systems. This is a model without counterpoint bars, just simple a fluvial model with oxbows, and I'm obviously injecting on the left side, and there's a producer on the right side, somewhere over there, and you see the patterns of how the fluid flows. We are doing this very simple flow diagnostic approach using this free software called MATLAB Reservoir Simulation Toolbox. So let's see what happens now if I add to the same model, if I add some counterpoint bars and take into account that most of these bars have heterogeneities associated with their downstream ends. So there is the model, and now you can see that the flow front is very different from what we saw on the other slide, and it's more complicated. Whenever I try to predict what's going to happen in a model like this, without looking at the simulation, I fail. So it's very important to not just build a stratigraphic model, but also flow simulate it and see what happens. We can have a look at this in 3D as well, injector at the top, producer at the bottom, and now you can understand a little bit better that these flow tongues are just looking for the nearest pod of higher quality or higher porosity sediment. And that's pretty much all I wanted to say. I think problems, there are many, but we can see them as challenges, and I think this can be an exciting time for us sedimentary geologists if we use the all these available tools to us to address many of these challenges. And if I was a student or a young professional starting today, I would focus a lot on these issues and opportunities. Thank you.
We have time for questions. Please use the microphones.
Thanks, Zoltan. Could you elaborate a bit on the bar type model and how the convolution of migration and the curvature in your model leads to different bar types? Just a little bit more on the mechanics.
You mean the point bar versus counterpoint bar?
And I followed your description of the occurrence of where the counterpoint bar would happen, but can you just talk a little bit more about the reasoning of the differentiation of bar types that comes from mapping as you made in those dynamic models?
Right. So if you are using a model, it's easy because you already have migration rate and curvature. If you are looking at natural examples, then you have to either measure migration rate and curvature or estimate migration rate based on the model. And then you multiply those, and you get the bar type index, and that the bar type index gives you basically the proxy for distributing grain size and ultimately porosity and permeability. The way I did it in these models is very preliminary, so there's no really making sure that I have this grain size and this porosity and this permeability at this location. That's future work.
Great. Thank you again.